introduce Piotr Szymczak, who is the same department as I am in the University of Warsaw, Department of Physics, and he is going to tell us how water dissolves rock.
Thank you very much, Konrad. So first of all, I would like to take this opportunity to thank the organizers of this great semester, Keith, in Beijing, but also Konrad here, and for giving me the opportunity to be here and also to present this talk to you. So I will be talking about the problem of dissolution in fractures and in porous media, in porous rocks. And most of this, of the things which I will be talking about are the result of our common work with Tony Lott from University of Florida. Tony was here about 2 weeks ago for 10 days. Okay, so the plan of the talk is the following. First, I would like to introduce the dissolution problem on the example of the fractured dissolution, because I think it's kind of maybe a bit easier to grasp than the porous media dissolution. Then I will move to porous media, and I will try to make the connection between the two, emphasizing the differences, but also the similarities between the two problems. And then I would like to end up with some open problems, which I think are quite challenging, but also really interesting and important from the application point of view. Okay, so the sort of systems that we would like to consider here are either fractures or porous media which dissolve as a result of the reactive fluid being flushed through the system, right? So here is a rock fracture in a big piece of rock, and the fluid is seeping through. And if this fluid is carrying some reactant, for example, if this piece of rock is calcite or limestone, and the fluid contains some acid, like carbonic acid in this case, then in many cases this reactant is able to dissolve the rock surfaces, in that way changing the geometry of the system. And the sort of questions which one may ask here is how would the morphology, the geometry of the system evolve over time, and what kind of patterns or structures are expected to be formed here with time. And the problem is, in general, pretty complicated because it involves a number of coupled processes. So first we have fluid flow in a complicated geometry. Next we have the reactant transport. Then we have chemical kinetics at rock surfaces. And on top of this we have the evolving geometry. So the geometry is changing, and the changes of geometry will in general be coupled to all of these processes. So we expect some feedback loops or nonlinear couplings between these components. Okay, so let me start first with the fracture dissolution problem, and probably the most famous example or most important example of the fracture dissolution is formation of caves along the fractures in limestone rock. And there was a long-standing controversy on how caves are formed, and the hypothesis which is accepted right now that they formed as a result of the dissolution of calcium carbonate contained in limestone by the water surcharged with carbon dioxide, with CO2, which forms a weak acid, carbonic acid. So this hypothesis was put forward only in 19th century, in 1830, by one of the fathers of modern geology, Charles Lyell, in his monumental work. I think it's 4-volume work, huge work, Principles of Geology. And as it usually happens with great ideas, at exactly the same time, there was another guy, French geologist Charles-Édouard Thiriat, who published the same thing, I mean the same concept, independently in small newsletter in France, geological newsletter. So at the same time, it sprang out in minds of two independently working people. Okay, so I would like to analyze this problem for a while. So the problem is the following: we have a fracture. We will not consider the whole system of fractures as it usually is in a real media, right? Because in a real rock, you don't have just a single fracture, but you have an interconnected network of fractures which are dissolving at the same time, and it all happens over hundreds of thousands or even millions of years. What I would like now to concentrate on is a simpler system where you just have a single fracture, one of these guys, right? And we'll be just interested in a very early stages of the dissolution process where the flow between these fracture walls is laminar, there is no turbulence, and it's all happening very slowly. And in such a case, one is tempted to simplify. And in fact, the simplest model which can be found in speleogenesis literature, so in the community which deals with the origins of caves, is so-called one-dimensional model, when one basically claims that everything which is important, all the important fields, physical fields in the fracture, depend on just a single spatial variable, on the distance from the inlet, which I called x on this graph here, okay, the distance from the inlet. So fields such as the aperture, which is the distance between the fracture walls, or the flow profile, or the reactant concentration, they would, in this model, they would just depend on x, right? So essentially, it boils down to saying that the fracture opens up uniformly, yes? Like the pages from the book. There is no variation along y, along the direction perpendicular to the flow. Of course, it opens the most at the inlet, where there is a lot of reactant which is not yet spent, and then it opens slower and slower as we go deeper. And this simple model has this, well, big advantage that it's analytically tractable, so you can calculate things on a piece of paper, and it's very popular in the literature. I mean, the first paper which introduced this was a famous paper by Weil in 1958, but it's still present up to this day, really, this model. So let me now go over this model, because it's a simple model, and then you would probably grasp the most important components, and then you can understand the whole problem. So there are four elements of this model. The first thing is that we need to describe the dissolution in a certain way. We need to be able to describe the dissolution in a quantitative way, and so we need to assume or find experimentally the expression for so-called dissolution current, which is just the number of dissolved molecules of calcium carbonate per unit area of the fracture, or of the fracture wall, per unit time. And it turns out from the experiments that the limiting factor in this dissolution process in natural fractures under normal conditions is the concentration of the calcium ions. So this process is a bit like the dissolution of salt in a glass of water, right? You can dissolve it as long as the solution is unsaturated. Then the solution saturates with salt or with calcium ions in that case, and the dissolution stops. And in the first approximation, you can just assume that this relation is linear, so that the solution current is some proportionality constant called the reaction rate times the undersaturation, the difference between the saturation concentration of calcium ions and the actual concentration at the fracture wall. The solution low like this. Now, when you have this, then you can, of course, also calculate the erosion rate, or the rate with which the fracture walls retreat, the rate of geometry change in a given place, which is just proportional to this dissolution current, with just an extra constant which recalculates the current or the number of moles dissolved into the actual volume dissolved. So one needs to multiply the dissolution current by the molar volume of each mole of CaCO3, right? To calculate it in terms of centimeters, not the moles. Okay, and then so that gives you the dissolution law, and now you also need to calculate the flow in this fracture. And what people do here is to assume thin film or lubrication approximation. So basically, you make use of the fact that the fracture is much longer so the length of the fracture, the lateral dimension might be about, say, 1 kilometer, whereas the aperture is like 0.1 millimeter. So there is a huge scale difference between the length and the aperture. So one can assume that it's a thin film, and then one can adopt the lubrication approximation in which one assumes that the flow profile is locally parabolic. So as if it was a flow between the two planar walls distanced by h of x. And then you get the linear relation between the volumetric flux or the flow integrated over the z dimension and the pressure gradient, where R is sometimes called the hydrodynamic resistance, and it's proportional to 1 over the third power of the aperture. Right? Just as it is in a normal Poiseuille flow. Okay, and the last element of the model, the fourth element, is the mass balance for the reactant, because you also need to calculate the concentration of the reactant in the fracture, because only then you can know how fast it dissolves. And this might be done just by simple mass balance. So you have your fracture, and you just calculate how much stuff is flowing through this dashed line, through that dashed line, here and here, and the difference between these two fluxes is equal to the amount of calcium ions released from the walls, which you know from your dissolution current. So you write it down, and it has a form of just convection reaction equation. For simplicity now, I am neglecting diffusion, the lateral diffusion, the axial diffusion along x direction, but I mean, it might be included. It's just more complicated mathematically, but it doesn't really change the conclusions. Okay, so these are the basic elements of the model. Okay, I would like you to ask if you don't understand something, because I mean, there is no point in my going on if I will lose you. Okay, so now when you have these equations, you can actually integrate them. In the simplest case, where you just assume that the flow is constant, so the fracture is very long, and there is something going on only at the inlet, so the flow is more or less constant during these early stages of the dissolution. And now if you integrate the transport equation, I mean, it's very easy, it's just the exponential, right? And you get this kind of profile for the concentration of calcium ions. And please have a look how it, I mean, have a look how it looks like. It's just exponential. It climbs up pretty steeply, and then it just reaches the saturation concentration. And the penetration length, or the length over which the saturation concentration is reached, is given by the volumetric flux over R, where R was, just to remind you, the reaction rate. And then if you put this equation into the erosion equation, so you basically integrate it over time, you get the aperture profile like this, which is just h0, or the initial distance between the plates, plus, again, some exponential, but this time with the amplitude linearly growing with time. But the most important thing here is this penetration length. You see that both exponents have the same penetration length, and really nothing is happening here in the fracture on the distances larger than a single penetration length. And now when you calculate this penetration length for the typical limestone fractures, you get a surprising result that is just a few centimeters, which means that with a model like this, you can only have something going on you can only get essentially a skin effect, something dissolving at the depth of a few centimeters, but you would never get the dissolution along the whole length of the fracture. So in this way, no conduits, no passages, no tunnels can be formed or caves cannot be formed in such a model. And this was noted by White and Longier 4 years after the original whale publication, that really the stuff saturates so quickly that you cannot understand the formation of caves with the simplest model of cave formation. So there is a paradox here, right? So I mean, the caves cannot be formed according to this.
So H0, you assume H0?
Yes, we just say that, well, there is certain H0 at the beginning. So at the beginning it looks like this. And then you introduce this reactive fluid, and then it begins looking like that, right? You are getting this.
And penetration depth is independent of H0.
Penetration depth is, I think, dependent on H0, because if I need Q. So there is Q in the penetration length, and Q is really velocity integrated over H. So there is this H sitting there, but this was calculated for typical fractures that are in the limestone rock, which are of the order of, as I said, 0.01 millimeters, right? So for these fractures, the flow is pretty small, and then you can calculate how deep the reactant goes in. Yes?
With regard to fundamental cave formation, underlying those equations and the way they model dissolution, etc., is an assumption of total uniformity.
Yes.
And the resulting equations have this exponentially decaying solution. So it's no surprise.
Yeah, I'm not saying, well, yes, it's not surprise because it was there in the model. Still, for the people at that time, it was a surprise because they thought that they have a nice model for cave formation, and it turns out that really they cannot dissolve anything because it decays exponentially, right? So, yeah, I mean, I agree with you that this is just a very simple observation from this model. It's nothing very, refined or something, yes.
And so you assume that this dissolution takes place kind of instantaneously. Does it take any time to dissolve this?
Why do you say
reaction?
No, it doesn't take place instantaneously. Yeah, maybe I have skipped over this point, so maybe let me explain this in some more detail. So you have these walls, and now you have to solve really 3 problems. Flow problems, to calculate the flow in each point in between the walls. Then the concentration problem, or reactant problem, to get the to solve the transport equation for the reactant in between these walls. And both flow and reactant, they relax, they come to a steady state on much faster time scales than the thing is opening, right? So for solving the flow and reactant transport equation, you just assume that the surfaces don't move. You freeze them.
What I was wondering is whether the flow speed can be large enough so that the reaction at the walls actually doesn't take place so easily. So the fluid penetrates much further before it could.
But that's already here, right? I mean, I think if I understand your question correctly, that's already here, that the penetration length depends on the speed. If you increase the speed, if you increase the aperture, then this Q goes up like the third power of aperture, and this effect is there, that the unspent fluid, so to say, penetrates deeper. So yeah, I am not saying it's a very complicated observation, but still it was puzzling, and still it was a problem for the people. And the way out that they could see, which you could probably also guess yourself just by looking at this differential equation, right? Because this side, the right-hand side, is linear, we are going to get the exponential, right? But so the way out for them was to say, so this must be the problem, right? That we have assumed the linear reaction rate. And the way out proposed by White in 1977 was so-called kinetic trigger mechanism, when they said, well, when you really look more carefully at the results of the experimental results of the calcite dissolution, what you see is that this dissolution current is not linear in the entire range of the concentrations, but instead it's linear up to some point, and then it switches to a nonlinear low, so it decays much more slowly. So there is the linear low here up to some threshold concentration, and then it switches to a nonlinear low with the power larger than 1. And of course, if you now solve the differential equation, since you are feeding it with the power law, you will get a power law as well for the decay of the concentration. And then when you integrate it with time, and you compare it with the linear law, you see that in the linear case, nothing is dissolving from more than, say, 1 meter for a fracture of 100 meters. But at the nonlinear case, at the same time, you have this tail, which is slowly dissolving over time, but the fracture is opening over the entire length, right? Because now you don't have any characteristic length scale.
Question. The flow rate is the parameter that you impose fixed.
Yes, you usually look for some characteristic pressure gradients in the rock, and then you say that the characteristic flow rate would be such or such, yes.
Yes, but that's the point. The more natural would be to fix the pressure gradient.
Yes, that's what I said at the very beginning. If the situation is like this, that the fracture is just opening here, but it's not opening over there, then the actual resistance of the thing, if you think in terms of electrical resistance, is just more or less the same, because this part is so much longer than this initial part that dissolves. So then you really can just assume that the flow is constant. But of course, as soon as you have the dissolution over the entire length, then you need to recalculate the flow each way around as the geometry changes, right? But the inclusion of the unsteady flow doesn't, if you calculate it, it doesn't get you out of this cave formation paradox with linear kinetics. The dissolution times are astronomical as well, I mean, longer than the age of the universe, right? So again, so the trick here is to say this would switch to nonlinear kinetics, so the dissolution will slow down. This means that the unsaturated solution can penetrate deeper inside the fracture because the dissolution is so slow near the saturation, and that's how we get this opening over the entire length, right? And this is more or less the accepted way out, or the accepted paradigm on why we have caves in the limestone.
What do they choose for n?
Oh, that's so in one of the classical papers it says that n is anything from 3 to 7, but generally close to 5. Just depending on the set of experiments that they have and so on. Basically, you have to realize that the limestone dissolution problem or calcite dissolution problem is a very complex problem with many coupled reactions going on. So what they do here is they are trying to find a limiting link, so to say, but really there are many things which contribute to this. So what they really do experimentally is they plot those dissolution currents on log-log plots, and then they are trying to fit some lines to it. But I think one may say that it is a confirmed, I mean, it is experimentally confirmed fact that there is this switch to nonlinear kinetics near the saturation. So I'm not claiming it's not there. It's there experimentally. What I claim, however, is what you were, I mean, the point that you were also raising is that perhaps the whole model is just wrong. I mean, that you cannot really use 1D model to describe this kind of a system. And you can only use 1D models where you are really expecting that the thing will open up uniformly, right? But in fact, I mean, the rocks are, of course, rough. And if this small roughness will trigger some instability, which would then lead to the focusing of the flow in some localized places, in some so-called dissolution channels, then of course using 1D model will be wrong, right? So I would like to analyze this problem. So is
people
1D model...
do people consider influence of the surface geometry on the dissolution itself rather than?
Yes, this is a different story. Yes, so actually now with AFM, they look at the dissolution process on a micro scale. So they see those peaks and they say, well, so what is the rate of the say dissolution of this peak here compared with a little mountain here and so on. So people try to get this kind of reaction rates from the first principles, from the very basic things, but this is that's a hard thing. In fact, it's a crystal, so it's also anisotropic. Different phases can dissolve with different rates. It depends a lot on local geometry. This is on a larger scale, so to say. We are just looking at some effective general rate. Okay, so you cannot use 1D model if you would have a process which can in principle break the symmetry along the other direction. And now if you look at the data, there are indeed many examples of non-uniform dissolution in fractures. So I will show you three. One is from the experiment. That's a beautiful experiment by Russell Detwiller, who was then 2003 at Livermore. And this is the first very precise experimental measurement of the dissolution in fracture measured as it was going on, right? So it was just, so the fracture was transparent. It was made from a transparent material which was dissolved by water, and he was measuring the aperture change by optical means as time went on. These are our simulations with Tonilet, and
this is the top view.
yes, exactly. Oh yeah, let me yes, exactly. So this is the top view, and the colors denote the aperture change. So the reactant is coming, say on this figure here, reactant is coming from below. Okay, it goes so the flow goes from down to up, and then the red is the other places where the dissolution is at the highest, then yellow, then blue, and then black are the places when there is no dissolution at all. So you can see that it does not happen uniformly. There are those channels being formed where the dissolution is focused because the flow is focused there. And the same thing is here in the simulations of a different system. And here is a example from the field, which I think is also quite nice because, as I told you, the caves begin their lives along the fractures. Now, fractures are essentially quasi-2D objects. So they have slot-like geometry. So the cross-section of a fracture look like this. But when you go to the cave, you never see a cave like this, right? What you see really are those huge cube-like channels. You see it here, and you see the initial fracture, which is cutting like through here, right? So along these fractures, when the caves are formed, the dissolution is also selective. Not all of these places where you look dissolve with the same speed.
Is that you in the picture?
Sorry?
Is that you?
No, it's not me. No. Also, you need to realize that the size of it is, of course, very large, right? It's a man size. So when there was a flow there, it was turbulent for sure, and so on. So I am not claiming that I can analyze this regime, but I can claim that the dissolution in fractures is non-uniform, and it leads to a formation of those localized patterns, which will eventually turn into something like this. Okay, so these are just examples of non-uniform dissolution in fractures. But now to really answer the question is, are the uniform solutions suitable or not? You have to go from 1D model to the 2D model, right? And that's, well, at least 2D. You can also go to 3D model, but 2D model is enough to analyze the instability of 1D solutions. So what we have here is a two-dimensional model of fracture dissolution proposed by Rajaram and collaborators at the beginning of 2000s. So what are the elements of this model? We still make use of the fact that the lateral dimension of the fracture is much larger than the aperture. So it is a quasi 2D object. So now we will average, we will integrate all the things over the aperture. So Q is the total flow integrated along this vertical direction. And here we again assume this lubrication approximation for the flow. So Q is proportional to the pressure gradient with a coefficient of proportionality, as if it was just between two plane walls, so h to the power 3. And the conservation, the incompressibility of the flow plus the depth average convection diffusion equation. So we take the three-dimensional convection diffusion equation in the fracture space, and then we average again along the vertical direction, getting a equation like that. And then we supplement it with the same kind of erosion law as before. And now when you have this extended model, two-dimensional model, what you can do is you can do a standard kind of linear stability analysis. You can now add small perturbations to these one-dimensional solutions that I was showing you before, and you can, so the perturbation will have an amplitude, say the concentration perturbation will have an amplitude delta C, will have the wave vector K, and will have a growth rate sigma, and the same for the aperture. You stick it into the original equations, you linearize with respect to delta C and delta H, and then you look for the relation between sigma and K. And it turns out that no matter what K is, so no matter what the instability wavelength is, sigma is always positive, which means that it's unstable over the whole range of the wavelengths. However, there is one wavelength when there is a maximum of this dispersion relation. So where wavelength which grows with a maximum growth rate, and this growth rate and the wave vector is proportional to the Damkoller number. So when you look for the wavelength which is maximally enhanced, this its wave vector will be proportional to the Damkoller number, where the Damkoller number is simply the ratio of the reaction rate to the fluid velocity in the fracture space.
What's gamma?
Gamma, yeah, sorry, that's my notational problem. So I have introduced this elementary volume of CaCO3, which was V, small v. I don't know if you remember that. If not, I can probably go back. It's here, for example, right? And gamma is 1 over. Sorry, because that was my older notation. Okay, now when you look at the numerical results, you indeed see this, that the instability wavelengths go down. Yes, it decreases as the Damkoller number is increased. So as you basically increase the reaction rate, this instability wavelength goes smaller and smaller, and that's in fact how we noticed that. I mean, we just have run some numerics, and then we noted that this sinusoidal perturbation is growing. So that's what made us do the instability analysis in the first place. Okay, and this is similar to a instability which was described before in the porous media, which was first described by Chadam Ortoleva at the end of 80s, which is called reactive infiltration instability. And the basic mechanism for this is the following, that if you have a small bump on the dissolution front, or the border between the dissolved and undissolved space, right, then the permeability is locally enhanced near such a bump, so the flow is faster. If the flow is faster, then the unsaturated solution penetrates deeper here, and the reaction speeds up in this region here, so this bump has a tendency to grow. So it's a classical instability mechanism, which is also present in the fracture. And then when you wait longer, then this competition, right, or this instability mechanism takes place again, but now between these perturbations themselves. If one of them is a bit longer or a bit larger than the other one, then the flow is faster here, and the faster flow means a deeper, larger penetration depth, so this one would grow faster and would concentrate more flow and so on. So this leads to the appearance of just a few active large channels and the gradual disappearance of the...
Does that actually, on that point, does that actually mean that the bigger flow is stealing flow?
Yes, it's stealing flow from the others. Yes. Okay. Okay, but I think the most important result is on this slide, actually, where we have compared 4 models for the fracture dissolution, which I was showing you today. So first, just a one-dimensional linear model, which has this problem of exceedingly long dissolution times. Then one-dimensional non-linear model with this kinetic trigger, and then 2D linear and 2D non-linear. Now what you are looking at here is the time on this axis and the flow. So here we impose the pressure gradient and we let the flow rise up. But you see that for a very long time the flow really changes very slowly, and then it goes up where the unsaturated solution breaks through to the other side. Yes, when the channels just reach the other side, then the increase of the flow is huge. And now, so these points where the increase of the flow becomes huge are called in the literature breakthrough times. Breakthrough times. So the time where the unsaturated solution breaks through to the other side. And you see that the breakthrough times, which are like a basic quantity that you would like to calculate when you analyze the dissolving fractures, depend a lot on the model. So they are very long for this 1D linear model. So for a 100-meter fracture, it's about a few thousand years. For 1D nonlinear model, it's smaller by an order of magnitude. And then for 2D model, it's smaller by another order of magnitude. But I think the important point is that the 2D breakthrough time is almost independent of the actual model of the kinetics, which I think means that this channeling mechanism is more important factor controlling the dissolution of the fracture than the actual differences, small differences in the kinetics that was claimed before. So I would say that this might serve as an alternative explanation of the cave formation mechanism. So you don't really need the nonlinear kinetics, although it is there, to get the breakthroughs in the reasonable times for large fractures, like kilometer-long fractures.
Why are these times so badly wrong?
What do you mean they are badly wrong?
Well, caves do not form 10 years.
No, this is for a 100-meter fracture. This is that's a small fracture.
Okay.
That's okay. Yes, this is okay.
And it is very thin.
Sorry,
It is very thin.
0.2 millimeter. I don't think it's that thin.
It's not a cave anyway.
Sorry.
It's not a cave.
Oh, it's not a cave. Yes, I mean it goes up maybe to 1 millimeter at the beginning, but then the things really speed up. Then the flow becomes turbulent and so on. And in fact, there are under large hydraulic gradients there are examples like that. So when you have a dam which was blocking some body of water and so on, so the pressure gradient is large, then the caves were gypsum were known to be formed over like 20 years or something.
But there's no experimental data to put on this plot?
There is no experimental data to put on this plot. It's hard to take the experimental data. I mean, for sure, if you take the large fractures like the kilometer long along which the caves are formed, so for sure you would find that the linear model is out. It just predicts the astronomical times, right?
Referring to some nice experiment that you were simulating.
Postdocs don't last that long.
No, experiments. I mean, so experiments. This is a different matter. This is a very small fracture, 10 centimeters by 8 centimeters. So this is just the laboratory size fracture, and then it of course dissolves no matter which model you assume, because it might take you a bit longer. It might take you a bit smaller. We have repeated the simulations for this particular fracture because the data was so nice, and we got quite a nice agreement with the experiments. But that's I mean, the problem is not on that size, right? I mean, the problem that geologists had was not on a 10 centimeter scale, but on this multi-kilometer scale, and they wanted some mechanism to really reduce this breakthrough times on a kilometer scale. Okay, and then let me just show you what's going on around these the solution channels. So what I'm showing you here is the concentration field, where red means unsaturated reactant, and blue and black is just completely saturated solution with calcium ions. The aperture field, which shows you the increase of the aperture in a given point, and the flow field, where just colors denote the magnitude of the flow. And so I think it's interesting to compare the concentration field with the aperture growth. So you can see that there are many more channels visible on the aperture field than in the concentration. This comes from the fact that the concentration goes into the channels where the flow is the largest. Right? So they compete with each other for the concentration. So the smaller ones are completely drained from the concentration, and it just concentrates in the longest ones. And the other thing which you can see, I think, is that there is kind of hierarchical structures of these channels. So there are many small ones. There are fewer intermediate ones, and just a few large ones. And it's a characteristic feature of fracture dissolution.
Flow field is velocity or flow rate?
This would be the Q. So this would be the integrated velocity, and this would be the modulus of it. So Qx squared plus Qy squared. Okay.
Why do you have such a distinct feature in your pictures that these channels are very separated, as opposed to the previous picture shown by somebody else, that those channels almost like talk to each other, not this one?
Which one?
Somebody else did work. Yeah,
This
like
one?
this one.
The experimental work, yes. So I
Your
think
channels are very much separated.
yes, the size is different. So this is, as I said, 10 centimeters by 8 centimeters. So from the beginning, these channels really feel the other side. So they don't. So the competition between them, leading to killing off the smaller ones, in such a case, is much weaker. Many of them will break through
But
eventually.
in that picture, you see, as if what you might call the weak channel at the bottom dividing into long channels.
Here, yes, the one here is divided, yes. Also, there is much more roughness here than in these figures here, which might also influence the thing. As I was mainly concentrating on studying, but I will show you the movie with some roughness where you also might see this kind of tip splitting. So this would be a movie. Hopefully, it will play. Yes. So that's the concentration. So you would see that.
What are the axes?
What?
What are the axes?
You are looking at the fracture from above, as before, and the fluid is going from above, so x-axis is down here, and y will be in that direction here. So the flow is now from up to down, and yes, and you could see this competition between them, right? And then eventually just one of them breaks through, and then the whole flow is in this.
What is the color code?
The color code, again, this is the concentration. So red will be the unsaturated solution, like the pure water. black will be solution completely saturated with calcium ions. So there is no longer dissolution because it's completely saturated. And blue and yellow will be something in between. Okay.
How come the exit channel is wider than the
Sorry?
How come the exit channel at the end of your simulation was wider than the inflow channel?
Let me, maybe I can play it again if I know how to, yes. So you are saying that the tip here,
When it breaks through, it looks as if it's wider than at the top.
Okay.
here, yes, that it makes this kind of kind of fan, yes.
Yeah.
Yes, so I think the overall shape of this thing will be. I'm not good at plotting in 3D. So I think the overall shape of it will be that you have to understand that it's not only growing sideways, but it's also growing in this vertical direction. So at the inlet, because such a long time has passed, it will be very steeply up, and then it would do this kind of thing. So the total amount of stuff will be conserved. So here is the inlet.
Wide but shallow, I think.
This is very steeply up at the inlet, and then it goes to this kind of, large nose at the outlet, because there is also the vertical dimension. I don't have
Okay.
So this is a 3D simulation?
This is a 2D simulation, but in this 2D,
There's an implicit third direction.
yes. So we are tracking h, which is the third dimension. But it's not an explicit variable, it's just the distance between the fracture walls, which is tracked by the code in this.
What sort of fluid velocity is involved in this?
Pretty small. So in the fractions, it will be like 0.1 centimeters per second or something like that. Okay, and now I don't really want to make the talk too long, so I will just mention that the problems in porous media very briefly, and then I probably prefer to go to the open problems, which I find more interesting, and maybe it will inspire you. So as I told you before, a similar instability was also reported much earlier in 80s. By many people in the porous media, and in fact it was known at least from 40s or 50s. It was known by petroleum engineers that when you insert the acidic solution into the porous rock under the pressure, and say that this rod here is your well, which you made there to extract oil from the ground, from the porous reservoir, right? But by drilling the well, you have made some damage to the sides. Maybe you have blocked the pores with little clay particles and so on. And now you want to open the pores because you want to extract the oil, of course, in the first place. So what they did, or what they usually do, is the procedure called acidization, when they pump acid under the high pressure. And it turns out that when you then make X-ray study of this piece of rock, it shows a very non-uniform dissolution by this acid. It shows this kind of wormholes forming. Again, the flow channels which open up preferentially, so the dissolution is non-uniform, and it's very useful for these engineers because these flow paths are just the perfect paths to then extract oil from these regions here, right? And also, these are very nice experiments just made by Dakot in the lab from his, I think, Nature paper in 1987, where he just dissolved a block of plaster by water, and then he inserted wood's metal casting, just the thing which you can insert into the pore space, and then it solidifies. Then you break off the plaster, and you have a picture of how the pore space looks like. And again, you can see these wormholes. So the fact that the dissolution of porous media was non-uniform was known for quite a long time, and not only in systems like this, but also in some other interesting systems like uranium rolls or terra rossa, but let me not go into detail now. Let me just say that when you describe the dissolution of porous rocks and fractures, then the equations have a very similar structure, with the role of aperture played by porosity. Porosity is just the amount of the empty space of the say fluid space in an elementary volume of the porous material, and all the equations can be kind of mapped one on the other. So when we begin working with fracture dissolution, we thought that it's enough just to take the papers from the porous rock community to understand our instability wavelengths as well, but it turns out not to be so. And then we understood that, well, the reason is simple. Even though the equations are the same, the actual base solutions, or those one-dimensional solutions, are completely different in fractures and in porous material. And the reason for this is that in fractures, so in systems like this, you have effectively unlimited growth at the inlet. So the profile can just open up as much as it wants at the inlet, and that's how you get this exponentially growing profile. So that's how the uniform profile evolves in fracture. It just opens up. On the other hand, in porous media, there is a limit to this porosity, because at a certain point, everything which was there to be dissolved at the inlet will be dissolved, right? So the solution would kind of hit the ceiling. So either it would be empty space here, or there would be just insoluble material here, and then this unspent reactant would move on inside the piece of rock. So let me just show you how it looks like in case of the fracture, right? It opens, in case of the porous media, it opens up, but then it hits the ceiling, and then the translating profile is formed, the invariant profile, the front, which just goes inside the porous block, right? So these profiles actually are different, and each of them is unstable, but these instabilities have a different physical characteristics, right? So if you look at both instabilities, they would have in general different wavelengths and different dependence on the physical parameters. So this was kind of like eye-opening for us, that it's not really the same instability in the fracture that you can see in the porous media as well. So let me maybe skip the comparison between the two instabilities, because it's really going maybe too technical. And I would just like to mention some open problems at the end, which I presently don't know how to attack, but which are really fundamental for this community, I think. So the most important problem, I think, is the breakthrough problem, which I kind of signalized before, which you can formulate in the following way: how long will it take for the fracture to open? So how long will it take for the longest channel to hit the other end of the fracture? And this is fundamental not only if you want to estimate the cave formation times, but also if you want to understand problems like this dam seepage problem, right? So you build a dam over some rock. It might be a soluble rock like limestone or gypsum, and you want to estimate for what period of time you are safe, and after what time it might, due to the dissolution, seep through. Of course, the hydraulic gradients here are much larger than in a natural fracture, so you have to be aware that it might seep through pretty fast. Yes?
In that right-hand picture, you have one of them in the middle, somewhat in the lead.
Yes.
So it is probable that that one will get there first,
Yes.
but it might not. Some other one may.
Usually in the fracture, I will show you the porous media competition in a moment. Usually in the fracture, what I find is that once something is in the lead, it would win. But I don't even know how to estimate the speed of a single one.
One of its competitors in real life may hit a more weaker rock.
Yes, so this is true. So here the noise is pretty small. The noise is just here to trigger the instability. You don't have like large, empty pockets in the rock or something. I think you can formulate it as a mathematical problem. You have more or less uniform fracture with just a very small noise. This front is being born. These channels compete. And now it's a nonlinear problem because they compete, they interact in a nonlinear way, right? It's no longer the linear stability problem, and you need to know how long will it take for the first guy to break through. And this problem is really closely connected with the question, what controls the shape of the finger? Which I also don't know, which seems to be like a fundamental problem. So you have a fracture which is now very long and thin. So very soon there is just a single finger growing because all the others were killed. And this finger has a certain width which seems to not change in time anymore, right? That's the aperture. So you see that here is this width of the finger, and how to calculate this width. Also, I think you can see here an interesting observation that the finger doesn't grow straight. It meanders, it goes sideways like that, right? You can see it here. You can also see it on the transverse flow map. So that's the flow map in that direction. Black means that the velocity is directed upwards, and red means that it's directed downwards. So you see here this oscillation. It goes up, down, up, down, up, down. And then at the tip, it distributes the flow, right? Throughout the whole fracture, it goes here, like a dipole here at the tip. So what is the shape even of a single finger, and how fast it moves, and why it goes sideways, why it meanders? I have a movie here which will show you the meandering finger. So now he is born, and you see it meanders in a funny way. So it really, the meandering is controlled at the tip itself. It's the tip that meanders, and the rest just follows, right? So why does this, and what controls the wavelength, which seems to be very regular, right? This is something which I don't know at present how to attack mathematically. And also the multi-finger case. So now I will show you the competition in case of the porous media, and I have changed the colors for a better contrast. So instead of black, now I have white, but you will see it pretty quickly. Oh. Yeah, I think. Yeah, so I think this is somehow screwed. Let's see if this would work. Yeah, you can probably see them. These are the fingers for the porous media. So I can play it again. You can see that they compete, but they also join up, and then they form the thicker ones, right? And there is a lot of things going on here, right? Competition between the fingers, also joining up, splitting, and so on. But still, at the end of the day, when you will plot the leading edge, what I mean by the leading edge is just the position of the tip of the longest finger versus time, and also the trailing edge. The trailing edge is maybe more tricky. The trailing edge is the position where the speed with which the red move. So the last point where there is black here. So red is just the completely dissolved region. So when you plot these two positions versus time, you see that they just grow with a steady velocity. So even though there are so many things going on in this system, right? It seems that there is something fundamentally very simple about it. So even though there is this non-linear interaction between the fingers, still the edge of this region is just growing linearly with time. But the problem is how to predict this speed, because this would give you the breakthrough time. And just to compare in the fractures, the situation is different. Yes, you have this hierarchical structure which I have told you about. So all the dissolution just is just focused in the few longest growing fingers. But again, if you will plot the speed of this tip versus time, it seems to be constant. And the question is how to predict its velocity. Okay. So just to sum up, I mean, I was trying to convince you that the dissolution of a single fracture is not a 1D process. It's never uniform, and that it's unsuitable to the perturbations caused by roughness, and that this is the mechanism which really controls the dissolution over longer time scales and which really controls the breakthrough time. And also, I was trying to point up to some problems which I don't know how to attack, which are in the nonlinear regime. And just let me acknowledge my main collaborator on this, Professor Tony Light, and two PhD students involved, Agnieszka Budek, and she was mainly working with network models of porous media dissolution, where you represent your porous media just as a network of little tubes, and then you let them dissolve. And we also made some analog models in microfluidic lab, and Hanna Mizinkiewicz, who is a joint student with a professor from geology department, and she works on more geological part of it. Okay, thank you very much.
Thank you very much, Piotr. Question, Asha.
I think this kind of problem is you need to do some fractal analysis. What is the fractal dimension? Perhaps spectral analysis. I mean, you see the periodicity of the fingers.
Yeah, so I was doing, so I had one paper, we had one paper with Tony on that problem here when we were looking at the distribution of finger lengths.
Mm-hmm.
And it is a power law with a certain exponent, which I don't know how to predict, but I can just, measure it. But still, it doesn't really tell me how to predict the speed of a single finger. So I think the problem which I would like to analyze first is just this, that you have just a single guy in a fracture, and you want to know with which speed its tip advances, right? It is similar in a way to other pattern formation problems like viscous fingering and so on, but these turn out to be hard problems. Even the classical viscous fingering, where you have a Safman-Taylor finger, right? It took people a lot of time to understand what controls the width of this finger. I mean, experimentally, it was known that it's taking up the half of the channel, but to actually prove it mathematically that this is the thing which would spring up in the experiment turned out to be hard. So I'm not sure if this would be easy. Just don't know.
Also, one more comment. It seems all related to DLA, diffusion limited aggregation. You see the same structures of.
Yes, there is a version of DLA which in fact looks very similar to this thing, which is the following version, that you are releasing your particles from above, and you have your substrate here, and you just allow the particle to stick on the top of the existing pile. So you have these small initial piles, and then you have your Brownian walkers here. When they go there, they will be killed. But if they go on the top, then they would stick, and then you have these columns growing, and they seem to have a very similar scaling properties to the channels. But the main problem is that the channel also have this width, which affects the speed, because
You don't see it in the DNA.
well, here it's just imposed from above, so to say. I mean, I just impose it in the model, right? But here it's just spontaneous, that all of the sudden you have a channel with a certain width, and it affects the speed, because basically how much the flow is focused is controlled by the ratio of the system width to the channel width. So you have to know what is the channel width. But we were thinking exactly along these lines, where we were doing this microfluidic experiment. So here is the network of channels, and you insert a low viscosity fluid into the high viscosity one, and this network of channels is imposing this anisotropy in the system. And we see very similar features to the fracture dissolution, with the scalings and with the competition between the different flow paths. Yeah.
No, you impose a fixed flow rate.
Mm-hmm.
So I can imagine that when the flow gets, for some reason, wide, then it will be in contact with the larger surface,
Mm-hmm.
and it will saturate quickly the same quantity of flow, of liquid, because you have a larger surface in contact with the liquid. And then once it saturates, then it cannot dissolve anymore, and then it would do kind of focusing, because it will not dissolve anymore the rock. And
So you're saying that there might be some stabilizing mechanism
Yes.
like this, and then you can find this.
It goes further, and then it will again, since the surface is small, then it will dissolve less, and the concentration will reduce. It will increase its dissolving power, and maybe fluctuate because of a mechanism.
Might be, but in this meandering problem, I don't really see, the change of the width. It's just the direction. It's like a river. There is some mechanism of meandering, but the funny thing is that there is no inertia in this problem. There is no mechanism that you went too far, so now you are going back, and so on. It's there is no inertia in the equations. They're just the first order in time. So I just don't understand at all. I was thinking a bit.
Do you know what's the relation between the meandering wavelengths and the width of the system?
No, I haven't studied it numerically. No. So maybe that's maybe
that wavelength must come from somewhere. How to?
Yes. Well, you can see the penetration length. The penetration length is more or less this width here, because that's what was initially dissolved, and this wavelength seems to be comparable to the penetration length. So but maybe something. One thing, if I don't put in the noise, because you can just dissolve thing which is absolutely absolutely noiseless. Of course, there is some numerical noise, so it's never absolutely noiseless. But over the time of such a simulation, this noise will not be amplified too much. If I do something like this, and if I just impose the initial small hole, so that I would promote the channel in a certain place, then it does not oscillate. So it is connected with the presence of the noise in the system. So there's another instability somehow triggered. I don't know what way.
The fact that everything is controlled by the tip is known in Healy-Shaw fingers, for example. There is an experiment where how fast the finger propagates.
Mm-hmm.
And it propagates with a given speed that you calculate very well.
Okay.
But every now and then you find a finger that propagates 4 times faster.
Okay.
And it was a mystery for a long time. And it turned out that these abnormal fingers have a tiny air bubble at the tip, so small you couldn't see. But the curvature at the tip determines entirely
Yes, I know these are beautiful experiments by Yves Couder.
Exactly.
With those small bubbles just put deliberately
Exactly.
in the tip. And yes.
He put them deliberately later on.
Later on, okay. So he
First,
first
he didn't
noticed.
know about them.
Uh-huh.
Discovered fingers that move much faster.
Yes. Well, I mean, for me, the amazing thing is that even though you may say, well, it's such a complicated nonlinear problem and so on, still, you know, at the end of the day, you get something really seemingly simple out of it. So there must be some statistical approach to
Mean
it.
field theory.
Mean field theory or something. Yeah, I don't know. I mean, I looked at similar problems, like, you know, viscous fingering, miscible viscous fingering. There was a nice talk by Maybook here during the workshop and so on, but they seem to be struggling with the same problems. It's not easy to describe.
But there is a similar problem of origin of the cracks themselves. So you have a fractured rock, yes, so you assume pre-existing cracks there, yes, and they also have some history, which also is described by these sort of hierarchical construction of them, yeah?
Yes.
And I would not exclude that the water plays some role in the process of creation of the cracks themselves. Yeah, so
Yes, but then it's a more complicated problem because you have elastic field on the top of the.
Yeah.
Yes, I know that you know similar things, as you say, you can just impose cracking at. So you have a piece of material, and then there are cracks growing here, and as you say, I mean the equations are different, but the general kind of competition between the cracks and so on, it shares many features with these systems. But the equations are more difficult because I think here is a bi-Laplacian of the field is equal to 0, and here is just the Laplace equation for the pressure. So it's a bit simpler.
Nature doesn't care about our problems.
Okay, any more questions? It's lunchtime then.